Hello everyone. Today our topic is per unit quantities, which is very important topic in power system analysis. Okay, so the various components of power system like alternators, motors, transformers, etc. have their voltage, power, current and impedance ratings in kilovolts, kilovolt ampere, kiloampere and ohms respectively. So it is very difficult to analyze a huge power system with different ratings. So it will be convenient for the analysis of power system if we take a common value for voltage, current, power and impedance. So that common value is called base value. Hence, for the analysis purpose, a base value is chosen for voltage, power, current and impedance. Then all the four ratings of the components are expressed as a percent or per unit of base value. Okay, so based on this point, we can state or we can define the per unit value as the ratio of actual value to base value. Okay, if I want the per unit value in percentage, simply multiply that with 100. So we get percentage per unit value. Okay, so you have to remember the formula. What is the formula? Per unit value is the actual value to base value. Okay, now, so the power system requires base values of four quantities. First one, voltage. Second one, power. Third one, current. Fourth one, impedance. Okay, so these are the four quantities. Out of these four quantities, two quantities will be specified. The rest of the two base quantities that we need to derive from the specified ones. Okay, right. So keep this point in your mind. Now, the per unit values can be analyzed in single phase system and three phase system also. Let us start with the single phase system. Now here power S and voltage V will be selected base quantities. Current I and impedance Z will be derived base quantities from selected base quantities. That means S and V. Now let us have the analysis. In order to have that analysis, firstly, let us assume that KVA base. Okay, so KVAB stands for base KVA, KVB stands for base voltage in kV, IB stands for base current in ampere, ZB stands for base impedance in ohms. Next. So, will be given with two quantities. So, what are they? Power and voltage. So, with that data, we can find the current relation IB as that power, that is kVAB divided by kVB, so that we can get the base current. Okay. So, that's why that means what happened? We have derived the first unknown base quantity, that is base current. Now it is the time to find the base quantity of the second unknown. What is that? Impedance. So this is the base impedance. So with our data, okay, so from Ohm's law, impedance is what? Voltage by current. I want my impedance in ohms, so that's why multiply that with 1000. Simply we'll get impedance in ohms. It can be further simplified because I know the expression for current, no? Okay, I got the expression for current. So substitute this IB here. Okay, so it seems to be like this. Now this KB term will go up so that we can get KVB square divided by the rest of the part KVAB by 1000. It can be written as kV base square divided by MVA base. So this is the formula for base impedance. So We are given with power and voltage, and we have derived the relations for base current and base impedance. Clear? Now, if I want to calculate the per unit value, what is the formula? Is the actual value to base value. Let us have the per unit value for impedance. That means we have to take actual impedance in ohms divided by base impedance in ohms. We got the values, no? So that's why we can have the per unit impedance. Similarly, we can do any kind of calculation for calculation using per unit quantities, like per unit value for current, per unit value for voltage, power. So like that we can find any quantity. Okay. Next one is a three-phase system. So here, in order to proceed with the three-phase system, we need to follow 2 points. The first point is, okay, the first point is VLN by VBLN is equal to VLL by VBLL. So what is this terminology? Here VLN refers line to neutral voltage. So VLL refers line to line voltage. So this numerator part is what? Actual value. This denominator part is base value. Okay, according to our definition, what is this actual value to base value? Nothing but per unit value. So that means, so what is this part? First part. First part is a per unit value for line to neutral. And second quantity is a per unit value for line to line. So that means the per unit value of line to neutral voltage will be equal to per unit value of line to line voltage. Okay. Next point is, so here also numerator is nothing but actual value of 3-phase kVA, and denominator is a 3-phase base kVA. Similarly, this second part is a kVA per phase divided by base kVA per phase. That means what is this part? This part is a per unit value of 3-phase kVA. This is the per unit value in per phase. So these 2 points we need to keep in our mind. Okay, that means three-phase system. In three-phase system, the line value of voltages and three-phase kVA are directly used for per unit calculations. Clear? Next, let us have the detailed discussion on per unit quantities in three-phase system. So let us have the first one. kVAB is a three-phase base kVA. kVB, line to line base voltage in kV. Next, IB is the line value of base current in amperes. We all know that in three-phase system, power is equal to what? Root 3 into voltage into current. Okay, so simply root 3 into what is the voltage? kVB, what is the current? IB. That's it. So where kVB is what? Line to line voltage. Okay, and IB is what? Line current. Okay, from this relation we can find the relation for IB. So what is IB? Simply this kVAB divided by root 3 into kVB. So we get the relation for IB. Clear? Next, in power system we are having mostly star connection. So why we prefer star connection over delta connection? In star there is a possibility of three-phase four-wire system that is not possible in delta. Okay, so mostly we'll use star connection. On that note, we are considering that the system is connected as a star connected system, and that too balanced system. So in a balanced star connected system, phase voltage is equal to line voltage by root 3, phase current equal to line current. So we are using that same information here. Okay, so now we are finding we have already found that current, no, base current is over. Now it is the time to find the base impedance. Okay, so now base impedance per phase means what? This is voltage. Okay, so this part is voltage. This part is voltage, and that to what? So we are measuring per phase, no? So where KVB is a line value, no? So phase value, if you want to calculate the phase value, what you do? Divided by root 3. That's it. Okay, so divided by IB. Done. So we find with ZB per phase. But I want my ZB in ohms. Then what I should do? I have to multiply with 1000. That's it. So if I rearrange, I can get this form. So this is the basic relation for ZB per phase. Now it can be even more simplified. So we already got the relation for IB, right? Okay, so we are just substituting the IB relation. That's it. With a simple calculation, we may get ZB per phase as KB square by MVA base. Clear? So here we have to keep one point in our mind all the time, that the impedance is always expressed as per phase. Right? So we got the per phase current, base value of current and base value of impedance per phase. Clear? Now, uh, like that we can calculate any of the quantities into per unit type. Okay, so once we clear with the base values, we can automatically find the per unit values with the simple formula. What is that formula? Actual value to base value. Now, the next important topic is changing the base of per unit quantities. So, so many people are having difficulty with this change in base. So now I'll tell you how simple it is. Okay, so exactly 2 to 3 minutes, this topic will be over. So let us see how easy it is. So let us have Z as actual impedance, ZB as base impedance. Clear? As you can see. Okay, so these are the two assumptions, Z and ZB. Now, per unit value. What is the formula? Actual value to base value. Done. Okay, so we got the relation for base value from the previous slide. No, we just recollected that. So if we rearrange, we'll get the relation. That's it. Z into MVA base by KVB square. That's it. Once you are done with this equation, rest of the thing is just like that, it will be over. Okay, so we have to take some measures, like in suffix, if we take old, that means it's a old kVA. Okay, so MVA old is a old base value, MVA old base value. Similarly, KVB new, MVAB new represents new base values. Clear? Old values, new values. Now, uh, let us Z per unit old is a per unit impedance of a circuit element calculated on old base value. Similarly, Z per unit is evaluated on a new base value. Now, we know in the previous slide we derived this relation. No, I just call back here. Okay, so now, therefore, simply what you do, let me take this. Okay, so Z per unit old, because we got the relation for Z per unit, no, instead of Z per unit, just simply write Z per unit old. Similarly here, actual value won't change, right? So similarly, so next part is the MVA base. So keep that with old value. Similarly, KVB square, substitute that with KVB old square. And similarly, do the same with the new. That's it. So two relations you got. What is the common element between these two equations? Simply Z. Clear? So that's why write the relation for Z from this one, from this equation. Similarly, write the relation for Z from this equation. Both are impedances, no? Actual values, no? So we have to equate these two terms. If we equate, then automatically we'll be getting the Z per unit new. That's it. If we rearrange, then it will be Z per unit old into KVB old by KVB new square. Okay, so this is the second term into MVB new by MVB MVA B old. That's it. So in this way, we can change the base value of per unit quantities. Okay, I hope you understand. If you are having any doubts and if you want any kind of a new topic to be discussed, just comment. I'll try to make that video. So if you like this video, please like, share, subscribe. Thank you.